Good day, my name is Jollibee Sanan. I was assigned to discuss about parallel projection theorem together with the similar triangles. So I want to prove what's so-called parallel projection theorem. The parallel projection theorem is going to be our tool to get a tons of similar triangles. Once you were in Euclidean geometry, we can talk about similar triangles. Similar triangles are going to allow us to do a couple of things. They're going to allow us to prove a Pythagorean theorem, which is a salient proof, one of which depends on similar triangles. The other similar triangles were going to allow us to do some trigonometry. We're going to talk about those things. So we must have some mechanism to generate similar triangles of various sizes. And so, today, we're gonna deal with this. So please stay watching. Let L, M, and N be distinct parallel lines. By the way, when we say something like this, it should be Euclidean. Because if you don't have a Euclidean parallel postulate, then you cannot say that L is parallel to M is parallel to N. You don't have that. So the theorem goes like this. We have L parallel to M parallel to N. And T is a transversal that cuts L, M, and N at A, B, and C. And T prime is some other transversal that cuts L, M, and N at A prime, B prime, C prime. Here is the claim. AB the ratio between AB and AC is the same as the ratio between A prime, B prime, and A prime, C prime. That's why we have this. To really prove what's parallel projection theorem, let's proceed to a lemma. Let us recall that we have L parallel to M parallel to N that cuts a transversal T at A, B, and C, and another transversal T prime that cuts L, M, and N at A prime, B prime, C prime. And let's pretend that AB over AC is a fraction that has P over Q is what we called rational numbers. So we divided this into equal parts. So we conclude that this part is the A sub Q equal parts, A sub B equal parts, and this one is A sub 0 equal parts. So each of A sub I, I plus 1 is equal to AC over Q. To continue with this theorem, to clear these things all, so let's proceed to a lemma. a lemma might clear these complicated things I discussed. So here's the lemma. Let L, M, and N be distinct parallel lines. So we have here, where should I put it? How about here? We have L and another M and another N is a parallel line, and L, M, and N that cuts by transversal T, L, M, and N at A, B, and C, and cuts another transversal T prime, L, M, and N at A prime, B prime, and C prime. Now, and another M and another N is a parallel line, and L, M, and N that cuts by transversal T, L, M, and N at A, B, and C, and cuts another transversal T prime, L, M, and N at A prime, B prime, and C prime. Now, we know that this side here is the same as the ratio between this side. And we know that this side here is the same as the ratio of this side. Now let's proceed to another T double prime that cuts T double prime. Let's make a T double prime. Sorry if not that straight. So let's make T double prime that cuts L, M, and N and forms another B double prime. Now let's create another transversal T triple prime that cuts L, M, and N and at the point C double prime. So as what we can see that this T is parallel to T double prime, parallel to T triple prime. And this side here, as what you can see, this is a parallelogram. It forms a parallelogram. So that means that this side here is congruent to this side. And another form of a parallelogram, so this side here is congruent to this side. You can see this is a parallelogram. It forms a parallelogram. So that means that this side here is congruent to this side. And another form of a parallelogram, so this side here is congruent to this side. Since this side and that side is congruent, so we concluded that the angle itself is also congruent to this angle. So we now form a side angle side. So that would mean that these two triangles created is a similar triangle. So, here is the claim for this lemma. So, by the lemma, we concluded that A prime sub I and A prime I plus 1 is equal to A prime C prime over Q. So we concluded that this A prime B prime over A prime C prime is just equal to our A sub Q prime A prime sub P all over A sub 0 A prime sub 0 A prime sub Q, and is equal to A prime C prime over Q times RP all over A prime C prime over Q times Q. So we could end up with P over Q, and in that case that AB is equal over AC. So in short, we prove that A prime by a parallel projection theorem, and as well as together with the similar triangles, we concluded that A prime B prime over A prime C prime is equal to AB over AC. So that's the end of our parallel projection theorem together with the similar triangles. Before I will end up, I just want to clear some things that A prime B prime over A prime C prime is equal to AB over AC. So this is what we called a parallel projection because we imagine projecting this line segment here, AB, is projecting to the direction of line L. And another line segment, BC, in the direction of line L. Until their shadows falls in a transversal T prime, we're going to allow us to create something, and that is helpful to us. It gives us a similar triangles all over places here. It allows us to construct something. So that's all I want to say about parallel projection theorem. Thank you so much for watching my video. Hope you learned a lot, and always remember that congruent parts of a congruent triangles are congruent.